Hello dear friends, welcome to this video. In this video, we'll be discussing one of the most important and interesting thing in the calculus, that is nothing but inverse function theorem. Without wasting much time, let us just go to the theorem. What does this theorem do in calculus? This theorem tells you about when the inverse will exist. We all know if the function is bijective, then the inverse exists. Then why this theorem is so much important? Right? What is something that this theorem tells special than being a bijective? This theorem give you the sufficient condition for the inverse of the function to exist in the neighborhood of the point in the domain, and that condition is the derivative of the function is continuous and it is non-zero at that point. That means, in simple word, if I try to tell, if I have a function, I try to talk from R to R only initially, and then we can generalize it. Suppose if I have a function from R to R such that its derivative is continuous at point A. Also, my f dash at A means the derivative at point A is not equal to 0. Then this inverse function theorems tells you that the inverse of this function f inverse would exist in a neighborhood of A. Okay, so what is the special in this? Inverse exists if it is bijective also. Why this derivative not equal to 0 or the derivative being continuous is so much important this theorem? Let us just try to see why in the next statement that I have given. Suppose if I have a single variable function and my f is continuously differentiable, means its derivative exists and the derivative is continuous. Also, it has non-zero derivative at A. Then the theorem states that my f is injective. This f is going to be injective, right? And more precisely, it is bijective if I consider the onto image in the neighborhood of A. And the important thing that this theorem tells is inverse exists. And what is the extra thing this theorem tells? That the inverse, whatever it is, that is also continuously differentiable in the point B, which is f of A, and the derivative of the inverse is actually nothing but reciprocal of the derivative. So this inverse function theorem tells you more than just being an inverse. This tells you, yes, inverse will exist in the neighborhood. And why we talk about the neighborhood? Because in the neighborhood, the derivative of the inverse would be same as what? Would be same as a reciprocal of the derivative of the original function. Right? So this is a beauty of inverse function theorem. It not only talk about inverse function, it talk about its derivative and how the derivative will look. It tells you about that as well. So apart from being bijective, when we said that it is continuously differentiable and the derivative was not equal to 0, the extra condition that we put, is nothing but my f dash at A is not equal to 0. This condition makes sure we can find out the reciprocal, and hence that reciprocal becomes the derivative of the inverse function. For an example, suppose if I consider a function like this, I consider the function f of x equal to x cube, right? What I observe is this function is 1 1. This function is on 2 as well if I consider the corresponding domain and codomain, right? And if I see this, my f dash at x, okay, for an example, let us just take x first of all. So it is 3x square, and if I consider f dash at 0, that becomes what? If I consider f dash at 0, then answer is going to be 0. So what I understood, in this case, I cannot apply my inverse function theorem because the derivative at the point 0 is 0, right? But what will happen if I'm unable to apply? That means something special should happen. Does that mean the inverse does not exist? inverse of this function do exist, right? Inverse of this function do exist. But what is a special thing that we understood over here? The special things. What is the inverse of this function, by the way? If you consider inverse of this function, what is f inverse of x? F inverse is nothing but cube root of x, right? And if you consider the derivative of this cube root, let us see what is this derivative. The derivative of this cube root is nothing but 1 by 3 x raised to, okay, the x should be over here, so it is x raised to 1 by 3 minus 1, and that I wanted to write at 1 by 3 x raised to 2 by 3, right? So this is nothing but the derivative. And now you can observe this derivative does not exist at the point 0, right? If I put 0, I get not defined. My f inverse 0 ka derivative is not defined. So this is something that was given. The inverse do exist, but whatever is the inverse might not be differentiable at that point. If the derivative is not equal to 0, it will exist. If the derivative is equal to 0, then inverse, if it is existing, it will not have the derivative at that point. This is the main idea behind the inverse function theorem, right? So what we understood, what is this inverse function theorem requires is your function should be continuously differentiable. It should have a non-zero derivative at that point. Then what will happen? Then your function would be invertible in the neighborhood of that point. Also, whatever is the derivative would be continuous. That means, in short, the inverse is continuously differentiable. And the most important thing is the inverse derivative would be same as reciprocal, or more precisely inverse of the derivative, right? This is something that inverse function theorem tells in short. Let us just try to get the proper definition now, right? I hope it is clear till now. If you have any doubt, difficulty, be free to ask in the chat box. See, this is the proper statement. Inverse function theorem. We are talking about a vector field function from Rn to Rn. This is a continuously differentiable function in an open set containing A, such that now when we talk about Rn to Rn, the derivative is nothing but what? It is nothing but the Jacobian matrix. So when do we say that is not 0? That means it is invertible, that is determinant of that is not equal to 0. Right? So derivative is not equal to 0, that means the determinant of that Jacobian is not equal to 0. So in the condition, it is determinant of f dash of A is not equal to 0. Then there is an open set capital V containing A and the open set W containing f of A, such that my f from V to W is continuous, has a continuous inverse, f inverse from W to V, such that it is differentiable, and for all y inside it, the derivative of the inverse is nothing but reciprocal of, or I will say inverse of derivative. Now if you see over here, this is a very important thing that we need to prove, right? We need to prove inverse exists, inverse is also continuously differentiable, and whatever is the inverse should satisfy this condition, right? So in this case, if you observe, on my left hand side, this inverse is nothing but the inverse function, and on right hand side, this inverse is nothing but inverse as a matrix, because over here this is going to be a matrix, right? These are the few observations that students should note. Let us just go to the proof of this theorem. I want to take the proof of this theorem. We will slowly create a wonderful proof. I hope you stay till the end, and if you have any doubt, difficulty, you can ask in the comment section. Okay, let us just start the proof. What I know is, as I said, the derivative of f would be a matrix, or more precisely, it is a linear transformation, right? It would be from Rn to Rn. So what I say is, I just give it a name. Let this capital L be the linear transformation, LT, linear transformation, f dash at A. Now what they have given me that my determinant of f dash of A is not equal to 0. Implies my capital L, which is the linear transformation, is non-singular. That means inverse of this linear transformation do exist, right? So therefore this implies me L inverse exists. Okay, now by using this, what I do, I define a new function g by using this L inverse and the given function f. Define a function g as L inverse composite f. Okay, what I have done is I have defined a new function g which is nothing but L inverse f. Now why this function is so much special? We will see shortly why this is the way to define g, because this will help us very much to prove what is required. But now, as we know, my f is continuously differentiable, right? My f is continuously differentiable. L is a linear transformation, so L inverse is also linear transformation. So L inverse is also continuously differentiable. Hence, my both the functions are continuously differentiable, implies me my g is continuously differentiable. G is continuously differentiable. Apart from this, if I think of the derivative of this g, what is the derivative of this g at the point A? Let's see. So my derivative of g at the point A is actually nothing but derivative of L inverse composite f at A. So this is nothing but composition chain rule, right? So this is nothing but derivative of L inverse at f of A composite with f dash of A, right? Now what we know? We know L inverse, it's itself a linear transformation. If we take a derivative of it at any point, the answer is going to be L inverse only, right? So what I'm using over here, I just keep it as a note. For any linear transformation, if you take a derivative at any point A, suppose a linear transformation I denoted by t, at any point A, it is going to be t itself, right? So similarly, this becomes L inverse. Apart from that, we have considered this f dash of A as L only. So it is L. So it is L inverse composite. This is actually L, right? This is what we defined earlier. Let L be the linear transformation f dash of A. So what I found, this is nothing but L inverse composite L, that is nothing but identity. So my dg of A is nothing but identity. So what is the determinant of this? So determinant of this derivative of g at A should be equal to 1, which is not 0. So what I observe is this g satisfy all the required conditions, right? So if the theorem is true, the theorem would tell that there would exist some v and w, and it would be true for this g as well, because it satisfies all the conditions. G is continuously differentiable, the derivative at that point is not equal to 0, right? So what I assume is, suppose if the theorem is true for this g, then I need to prove then it must be true for f. This is a point of confusion, might be there with the students. But suppose I just write it like this. Suppose if the theorem is true for this g, we will prove it. If assuming this help us, then in the next step we are going to prove this theorem is true for g. But for now, let us just assume that the theorem is true for g. Will it help us to prove it for f? That we are seeing. Okay, suppose this theorem is true for g, then what will happen? There will exist v and w such that my g from v to w has continuous inverse g inverse from w to v, and the derivative g inverse derivative at some point y, for an example of w, would be same as what? Would be same as G dash at G inverse of Y, and this matrix should be taken inverse for all Y inside W. If this theorem is true for G, then this is going to happen, right? And by using this, I will try to prove the theorem for F. Okay, so this is true. We are assuming that it is true for G. Now we talk about F. How we defined F, by the way. My G was nothing but L inverse composite F. So what is my F? Therefore, we have G is like this. Therefore, my F is nothing but L composite G. Now since L is invertible, G is also invertible by the assumption. So I can have my F inverse do exist, and that is same as G inverse composite with L inverse. Right. So this L inverse should start from L of W. So if I applied L on it, it will go to W. Now this G inverse will take this W to what? W to V. So this is for L inverse and this is for G inverse. So ultimately what we found my F inverse goes from LW to V. Right. So we found the neighborhoods LW and V. Now the part to prove, in the theorem we wanted to prove F inverse exists. Is it continuous? That is something we need to check. Now since my linear transformation are differentiable, differentiable implies continuous. Since my L inverse and G inverse are continuous, implies whatever is the composition, that is F inverse, is also continuous. So inverse exists, it is also continuous. Okay, this CT means continuous. Now what is left? Inverse exists, inverse is continuous. We talk about its derivative. Let us just talk about derivative of this F inverse. So I consider derivative of F inverse at a point, for an example, say x. So what is the same as? Derivative F inverse is what? F inverse is this. So derivative of G inverse composite L inverse at x. So this is same as what? I should, okay, it is fine. It is just a notation, right? Taking x or y is totally fine. So this is same as what? Chain rule, right? So it is derivative of G inverse, chain rule, the derivative of G inverse at what? At L inverse of x. Compose it with L inverse derivative at x. Okay. And after that, if I see, this is same as what? My G inverse derivative. Do we know what is G inverse derivative? By the assumption, G inverse derivative at any point is same as derivative of G inverse of phi whole inverse as a matrix. So this thing can be written as G dash at G inverse. Now what is the inside part? That is nothing but L inverse. So compose it L inverse of x, and whatever we get should be taken inverse. Now since L inverse is a linear transformation, this is a linear transformation, so the derivative is going to be itself. So it is nothing but L inverse only. Now it is B inverse A inverse, that is same as L composite G dash G inverse composite L inverse x, the whole derivative inverse, right? Very good. This part is also okay. Now what we know is, we know F inverse is what? F inverse is nothing but G inverse L inverse. So this G inverse L inverse could be replaced by F inverse. So in the next step I can write this is L composite G dash at F inverse of x and whole inverse. Now the only observation left is nothing but what we have on this side. We have derivative of f at x, f inverse of at x. The only observe that is left is nothing but this. What is the same as? L composite G dash. L composite G dash. we know that f is differentiable, right? Okay, if I see this case, this implies my f dash is what? My f dash is nothing but L dash at g of x something. Suppose if I consider x, composite g dash at x. Now, as we know, my L is a linear transformation. So, derivative at any point is actually same as that thing itself. So, it is L composite g dash at x, right? So, we found my f dash of x is same as L composite g dash of x. So, L composite g dash of this is actually same as my f dash at f inverse of x. The whole inverse is a matrix. So, f inverse derivative at x would be same as this, and which was nothing but the required. So, what we understood over here is, if I assume that my g satisfies the theorem, then automatically my f has to satisfy the theorem. So, what we understood, proving that g satisfies theorem would automatically prove the theorem is true for any f. And proving that g satisfies is very easy, right? So what we are going to do now, whatever we have assumed, that suppose if the theorem is true for this g, we are going to prove that yes, it is going to be true for this g. Hence, from that we will conclude that the theorem is true for f, right? So what is my claim now? My claim is, whatever I have assumed, I'll just claim it. My claim is to prove the theorem for g. To prove theorem for g. Okay, so now our task was to prove it from f. From that we will prove it for g. Okay, so let's just have to the bigger proof now. So we have multiple things with us. Let us just start. What we know about g? We know multiple things about g till now. My g was nothing but what? My g was defined as L inverse composite f. After that, we understood that if I take derivative of this g at a, then answer is going to be equal to identity. Over here, this L is what? L is nothing but f dash of a, right? This is where things that we have done. So this statement tells me that the determinant of g dash of a is equal to 1, hence it is not equal to 0. These are the few things that we can observe till now. Apart from this, one thing that we can see, the determinant exists at the point A. If the determinant exists at the point A, then by the definition of derivative, we have the limit h tends to 0 mod of, or the norm of, g a plus h minus g of a minus derivative of g of a, whatever is that matrix, at h divided by norm of h must be equal to 0. What we know is, we know that this g dash of a, that is this part, is actually nothing but identity. So in the next step, I just use that. So this becomes my limit h tends to 0 mod of g a plus h minus g of a, identity times h is nothing but h divided by norm of h, that must be equal to 0. And after this, what I see is it ever possible that my g of a plus h is equal to this part? I'm trying to observe whether this can be ever equal to g of a for any value of h. Can it ever happen? Let us just see if it happens and what is the case. If my g of a plus h is equal to g of a for some h, then what will happen? If it happens, then I consider the limit h tends to 0. This becomes what? This yellow part that I have highlighted becomes 0 minus h upon mod of h, and that becomes equal to 0. Now if I see, that is nothing but limit h tends to 0, that is nothing but mod of h upon mod of h, that is equal to 0. I can cancel this. I get 1, 1 equal to 0, 1 equal to 0. This is nothing but contradiction to the fact that my 1 is not equal to 0. Therefore, what I understood from this, I understood that my g of a plus h should not be equal to g of a, right? It cannot be equal to g of a. So indirectly what I understood is there is just a neighborhood around a such that the value of that g is not equal to g of a, right? There exists a neighborhood around a such that my g of a will not be equal to that value. Let me just try to write this. But ultimately what I was trying to see, I can find out a place around a such that it will not get the value equal to g of a, right? Because if it get the value, I get some contradiction, right? So based on this, we try to find out a neighborhood of a which satisfies some condition. Let us just try to write those things. So we choose a closed set U around A with the following condition, with the following conditions. What are those conditions? There are multiple conditions that need to be satisfied by this set U. The first condition that we observe, that my g of a must not be equal to g of x. That means no value should get overlap with g of a, and this should be true for all the points x inside that u. But if x equal to u, it will be true, so I just remove a. So u is a neighborhood of a which satisfies this condition. That means it will never take the value g of a except at the point a, right? So that is nothing but the first condition, and this could be is possible because we have seen if it takes at some other point as well, then we get some contradiction. Very close to a, we can find out all those points which will not take the value g of a again, right? So that is possible. Then my second assumption, I will choose u which satisfy all the conditions. So what we can do, if it does not satisfy that condition, I'll make my u very small and very close to a, right? I'll take it as small as possible until I get all the conditions satisfied. We know that my determinant g dash of a is not equal to 0. Then if it is not equal to 0, then I can find out even a neighborhood of it where the determinant is also not equal to 0. So my second condition is determinant g dash of x is not equal to 0 for all x inside u. This is possible since my g dash is continuous. If it is continuous and at some point it is not equal to 0, I can have a neighborhood around it where it is not equal to 0, right? Okay, and after that as well, we have the third condition that should be true for every point in the domain, that my half of mod x1 minus x2 should be less than equal to mod of gx1 minus gx2. Again, since my function is continuously differentiable, we can have a domain around A which satisfies this condition. Since my g dash is continuous, we can have this condition as well. This condition has been proved earlier in the Spreevac. You can use that proof to understand why we took this. But with these three assumptions, we have chosen our u, right? So my u should be selected in such a way it satisfies all three conditions. If it does not satisfy, I'll reduce the value of u. I'll just go more close to a, right? And over here I have considered u. Let us just try to go for the proof now. So what I have u. So let me just try to draw this. So this is my set, suppose u. I consider it as a rectangle. My a is over here. This is set u. Now on this u, I apply my g. What I get after applying g, I get some other set, right? So that set might look some random set, right? I'm just putting some random things. I just want to be more smooth like this. Okay, so this is the random set that I have drawn. This set is nothing but my g of u. since A is inside U, there would be somewhere G of A as well, right? Okay. We just try to draw and understand what is actually happening. Now, what are the two things I will see? First thing that I will notice, what is the minimum distance between G of A and the boundary of this GU. For an example, in this diagram, what I can observe is the minimum distance is actually somewhere over here. This is nothing but the minimum distance, right? I call this minimum distance as L. So I have considered L is nothing but, let small l be equal to the minimum distance between G of A and the boundary of G of U, right? So I have considered L, which is nothing but the minimum distance between G of A and the boundary of A. Apart from that, I consider one more value. That value is nothing but M, and that is nothing but minimum thing between all distance between G of X and G of A. Now let us just try to see what this actually. Over here G of A, we know A is fixed. What is this X? X comes from the boundary of U. That means if I consider any point on the boundary X, it will go somewhere on this GU. For an example, suppose it goes over here. This is G of X. This way, I will consider all the points on the boundary. It will go somewhere on the GU, and what I'll do, I will find out distance between GA and such GX, and whatever is the minimum distance, I will consider that as my small m. Now the question is, my this m, since I am considering minimum, can it ever be equal to 0? The answer of this question is no. We should note this. We should note this because it is an interesting part. That note that my m is not equal to 0. Because suppose if my m is 0, that means what? There exists some point on the boundary such that my mod of G of X minus G of A is equal to 0. And when this distance between G of X and G of A is 0, this implies me my G of X must be same as G of A. And which is not possible. Why? Because we have considered U such that my G of A can never be equal to G of X for any point except A. Now we definitely know A is inside it, not on the boundary. Hence, what happens is my G of A, which is a contradiction to 1, right? One that we have considered in making that. So what we understood, the value of M will not be equal to 0. Similarly, my this L, that is distance between G of A and the boundary, is something non-zero. What we do is, now I have two values, L and M. By using this two value, I create one more new value, that is nothing but D. Okay, interesting part. Difficult, yes, we are learning something difficult, but it is interesting. We create one more number, L, which is minimum of both the numbers, that is L and M. Okay, it is minimum of L and M both. Now, by using this, I create a new set W, which is actually nothing but the ball around my G of A with the radius of D by 2. That means what? If I try to see this, I will draw a ball around this G of A, and the radius of this ball is going to be D by 2. Right? So this G of A is going to stay inside this G of U only. The ball, this W, this sky color W is going to stay inside G of U only. And it is not going to have any point G of X where X is in the boundary, because my M is minimum of that and my D is minimum of M as well. So what I know is my D is less than or equal to M, and D by 2 is even strictly less than M, and my M is minimum, that means it is less than equal to mod of g of x minus g of a for all x inside the boundary of u. Right, so these are the few things that we have observed. What we have created, we created the set w. Now this set is a very important thing for us, because in the theorem we wanted that set w. By using w we are going to create v as well, but for now we will prove that for any point in the w there should exist a unique point x inside u, which is a pre-image of it. Okay, so for now we will prove, we will show that for any point, for any y inside w, there exists a unique x inside u, there exists a unique x inside u such that that x work as a pre-image for this y. Okay, so I need to prove this. So what I do for any x, right? So I consider for any y inside w, so I am considering any random y. For this I will define a map, define small h, a new map. I am defining small h as a map from this u to r real numbers, as this h will take any point in u to the norm y minus g of x square. Okay, so what is this norm square actually? Actually, the h of x is defined as what? That is nothing but sum. Since this it is square, so the square root part will go. So it is sum I running from 1 to n yi minus gi of x whole square. Right? As we know, the norm functions are continuous. It is continuous on the closed set. Right? In this case, it is continuous on the closed set. My h is continuous function on closed set. It is a distance function actually, and distance functions are always continuous. So it is continuous on the closed set u. Since it is continuous on the closed set, h has a minimum value inside u. Has minimum value in u. Now this h can have a minimum value anywhere inside u. It might be inside u, or it could be even on the boundary of u. But what we see is, if suppose it has a minimum on the boundary, what will happen? If this h, if this h has minimum on boundary of u, then there will exist some x on the boundary of u such that my h of x would be less than every value of h, or less than or equal to, more precisely. But my h of x would be even less than h of a also. Right? A is the point which is our center. Right? So if my h of x is less than h of a, then by the definition, the norm of y minus g of x becomes less than norm of y minus g of a. Right? And where this y came from? Y was any point in the w. Right? Y was at any point in the w. Now if you observe carefully, my y minus g of a, and y is an element of w. How w is defined? W is nothing but ball of g of a with the center g of a and the distance d by 2. So if y is an element of w, what we know is, since my y is an element of w, which is nothing but ball with the center g of a and the radius d by 2, that means distance between y and g of a, that means this mod of y minus g of a should be less than d by 2. Therefore, my both of them, that is my norm of y minus g of x is less than this norm of y minus g of a, also that is less than d by 2, right? This is something that we found, that my both this mode should be less than d by 2. Now let us just consider something else. We should get some either contradiction or we should not get a contradiction. Let us just see what can happen if I consider distance between g of x and g of a. What is the speciality about x? X lies on the boundary of this u, and we have something for the boundary of u, right? What we know, for any x on the boundary of u, the distance between g of x and g of a should be greater than this m, or more precisely it should be greater than d by 2, right? It should be greater than the d by 2, right? So that means this thing should be greater than d by 2. Okay, and what else we know? Okay, more precisely it is not greater than d, but it is even greater than d, right? So that d part would be very helpful to us. So it is greater than equal to d, because d by 2 might not give me contradiction, but d will give. So it is greater than d. Also, by triangular inequality, this is less than or equal to, mod of g of x minus y plus mod of y minus g of a, right? And we know both of them are strictly less than d by 2. So d by 2 plus d by 2. And over here we had d is less than equal to mod of g of x minus g by a. And if I see this, what I found is my d is strictly less than d, which is a contradiction to the fact that my d was equal to d, but we are getting d is less than d. So what was my assumption? My assumption was h has minimum on the boundary of u. So it could not have. Therefore, where it must have the minimum? Therefore, my h has minimum in the interior of u, right? So it has a minimum in the interior of u. So let there exist x inside the interior of u such that the minimum of h is at a, but sorry, x at this x. So minimum of h is at a. That means my h attains optimal value at x. We know that whenever a function attains the optimum value, the derivative at that point must be equal to 0, right? So we found the derivative of h at x must be equal to 0, since my x is nothing but the optimum value, right? So what is my h of x, by the way? My h of x was defined as summation of yi minus gix whole square. I was running from 1 to f, right? And if I say the derivative of s, derivative is actually nothing but the gradient and that inner product, but I just consider all partial derivative. If the derivative is 0, all the partial derivative must be equal to 0 at that point x, right? So I consider the partial derivative, that is nothing but I running from 1 to n. 2 derivative of this is nothing but x square derivative, and then by the chain rule it is derivative of gi, but jth order derivative, partial derivative, right? So this must be equal to 0. Okay, so this is something that we found. If that is 0, derivative is 0, all partial derivative at x are 0. Now by using this, what we can see, we see that my dg of x, what is this dg of x, by the way? My dg of x is actually nothing but that matrix dg1x, first order derivative means first coordinate derivative, second partial derivative, dot dot dot, third partial derivative, and dot dot dot, d1gnx, d2gnx, dot dot dot, dngnx, right? We know the derivative of g would look like this, and if I multiply this dg of x with a column matrix y1 minus g1x, y2 minus g2x, and okay, one more thing, over here this square should not come if I take the derivative. Okay, and dot 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 yn minus gnx. If I take the product of this matrix with this column matrix, what would be the answer? By using this, I call it as star. By using the star, can you all observe the first row with the first column over here, the column, this column is given as 0 by using that star, because this is true for all j, right? So by using that first row, first column, by using that star, we can observe that product is actually given as 0. So similarly, second row's column is also 0, dot dot dot, all are 0. Is it fine? So what we understood is, by using this, we understood one thing, that if I multiply that matrix with this new column matrix that I have considered, I'm going to get answer as a 0 matrix. Okay. Now let us just see what can happen if the answer is 0. What we know about this derivative? This derivative has determinant not equal to 0. This is not equal to 0. That means what? That means that is a non-singular, that is, it is invertible. If it is invertible, what we know? Originally we know that if I have ax equal to 0 and I tell you that a is invertible, if I call it that a is invertible, then what happens? Then this x must be equal to 0, right? So that means that column matrix is equal to 0. That means my y1, or I more precisely yi minus gi of x must be equal to 0. Therefore, my gi of x must be same as yi. If I consider it like this, coordinate wise, g1x, comma g2x, dot dot dot, comma gnx, then the answer is going to be y1, y2, dot dot dot, yn. And that is actually what? That is nothing but my g of x is same as y. Right? So my g of x is same as y. Hence, what we actually found, the pre-image of y is nothing but the point at which my function takes the minimum value. My h, wherever that h took the minimum value, that is nothing but the pre-image for the y. Right? The proof is big, but yes, it is simple. I have tried to make it as simple as I can. So what we have do is, so the proof is still remaining, but still, till now what we have we have done that y is an element of w. We were able to find x inside the interior of u such that g of x equal to y. Still, we need to prove it is unique x, right? There should be unique x. Here we found existence of x. Now we talk about the uniqueness of x. Now, for uniqueness of x, suppose there exists some other point x1 x12 inside u interior or u such that my g of x1 is also same as y. Now, since for u we have some condition, while selecting u we had made some condition. By condition 3, half of x1 minus x2 was less than equal to gx1 minus gx2, right? So by using that, my half of mod of x minus x1 is less than equal to mod of g of x minus g of x1. So my half of mod x minus x1 is less than equal to gx1 is y, gx1 is again y, so that is nothing but 0. Therefore, my mod of x minus x1 is 0, which implies my x must be same as x1. So for every point in W, there exists a unique point inside interior of U, right? So we were able to prove this. Now we got one set W. Now we want another set V, which is a neighborhood of A. So let us just define that A now based on whatever we got. Now we define a set V, which is nothing but where we know where the pre-image lie. Pre-image lie inside U interior. And I'll take, since it is a pre-image, I'll consider it intersection with all the pre-images. Right? So this will make sure that my function G from V to W is bijective, because it is onto for sure, and since for every point there is a unique image, that makes sure it is 1 1 as well. Hence my G from this V to W is a bijective function. If it is bijective, therefore there exists inverse G inverse from W to V. So as I said earlier, to become a bijective, it is enough we can get now inverse. But what is an extra thing that we have learned in this theorem is, this theorem tells the inverse exists, inverse is continuous, and the derivative is also given by the formula. Right? The derivative is nothing but reciprocal of the original derivative. Right? So these are the things that theorem tells us extra. Okay, now we found this G inverse is from W to V, it exists. Now our task is to prove that it must be continuous. While assuming the points we have, while assuming U, what we have considered, for any point in U, my x1 minus x2 half is less than equal to mod of gx1 minus gx2. This is something that we assume for every point. So it is true for every point x and y inside x1 and x2 inside V. Right? Since it is true for every point inside U, sorry, it should be true for every point inside V as well. Right? So I just take this 2 to the other side. So it is x1 minus x2 is less than equal to 2 mod gx1 minus gx2. Okay, and after this, since I want to talk about G inverse, which is there inside W, it starts from W, so I should talk about W, right? So every point should get inverse now. So I write this x1 can be written as x1 is there inside V, right? For this is true for x1 and x2 inside V. So V x1 and x2 can be written as inverse of some point. So it is y1 minus G inverse of y2, which is less than equal to 2 mod of y1 minus y2, right? And this y1 and y2 are actually the points inside W, such that my gy1 or gx1 is same as y1 and gx2 is same as y2. But if we see this, this is very interesting, right? If I say my this is less than equal to 2 times this, then for every epsilon greater than 0, there will definitely exist some delta, right? Hence, this implies me my function G inverse, whatever it is continuous, because it satisfies epsilon delta condition. This could be done by the students why it is continuous by using epsilon delta condition. So G inverse exists, it is continuous. Now came the last part of the proof, in which we'll talk about derivative of the inverse. What is something that is left to prove? Now we need to show that G inverse derivative at any point y must be same as what? It must be same as G derivative at G inverse of y, whatever is this matrix, should be taken inverse. And this should be true for all y in my domain, that is nothing but W. Okay, so this is something that we need to prove. Now to prove this, we will be using that my G, which was composition of L inverse F, is differentiable. We have my this G is differentiable, right? We know that G is differentiable for sure. Suppose it is differentiable, so it must be differentiable at all the point, as L inverse and G are differentiable at all the point. So it is differentiable at the x also, such that my G of x is same as the y. Since we want to prove for every y, I consider that y over here, right? So my G is differentiable at x, such that my G of x equal to y. Since it is differentiable, by the definition of differentiability, I can write my G of z if it is differentiable, it has a good approximation, right? It has a good linear approximation. So my g of z is same as g of x plus the derivative of g of x at z minus x plus the error function at z minus x, where this error function is special. This error function at z minus x divided by z minus x mod will tend towards 0 as my z tends towards x. Okay, so this is nothing but the by definition of differentiability that we learn actually in SY. This will happen, right? So what is this actually? We here, this is nothing but derivative, right? So this would be some matrix. This is some matrix. I want to think about this matrix. So I just call this matrix as J. So it becomes easier for me to write. So that is nothing but the J. So I get my G of Z. I take that G of X to this side. So it is minus G of X is equal to J at Z minus X plus error function at Z minus X. Since we know this J is actually nothing but working as an identity, right? It is some matrix, sorry, not identity. It is identity if X equal to A, right? So it is not identity for sure, may or may not be, but J is some matrix. Also, the determinant should be not equal to 0, right? It is differentiable, it has an inverse. So now this J is invertible. We take the inverse of J on entire this last equation. So I get J inverse at why it is not equal to 0. Do I need to prove it? I think this is one of my assumptions, right? We have taken that u such that determinant of g dash of x is not equal to 0 for all x inside u, right? This is over one of the assumption while considering u. Now you can see why we were so much interested in so many restriction on that u, because all the restrictions were used somewhere, right? This implies me my determinant of j is not equal to 0, hence it is invertible. I multiply by the inverse on both the sides, so I get gz minus g of x is same as the inverse will go, so it is z minus x plus j inverse of e z minus x, right? So this is something that we found. After this, I want to talk about g inverse, not g. So what I know is my g of x equal to y. Also my g of z must be something, so I call g of z, say it is gamma. So what I get, my last equation becomes my j inverse of g of z is nothing but gamma minus g of x is nothing but y is equal to z is nothing but g inverse of gamma minus x is nothing but what? My x is nothing but x is nothing but g inverse of y plus j inverse composite e of z minus x. The z minus x is nothing but what? Z minus x is nothing but g inverse of gamma minus g inverse of y. Okay. Okay, let's go further. After this, what I see? After this, I can write my g inverse of gamma, my g inverse of gamma is same as g inverse of y plus j inverse of gamma minus y minus j inverse composite e at g inverse gamma minus g inverse y. Okay, can you see something like a definition again? Can you observe that definition occurring again? If I write this is nothing but my new error function, I call this as E1. In the next step, I'll call that as an E1. This is a new error function at G inverse of gamma minus G inverse of Y. Right? So this is something like a definition of derivative, and this tells me that it is differentiable, and the derivative of this derivative at y is equal to j inverse if the error function do it works, right? If the error function works well, that means limit of gamma tends to y e1 at g inverse of gamma minus g inverse of y divided by gamma minus y. If this is equal to 0, then I'm done with the proof. That means this part would be true then. If the error function work, everything is good, right? So let us just talk about the final part, that is nothing but the error function. If my gamma goes to y, what will happen? If my gamma goes to y, sorry, I should select the pen. First of all, if my gamma goes to y, what are the things that will happen? If gamma goes to y, my g inverse of gamma will go to g inverse of y. Since my g inverse is continuous, it will happen. It is a continuous function, then it will happen. Now what is g inverse of this? That means my x goes towards where? My x goes towards, no, not x, z goes towards g inverse of y is nothing but x, right? Also, my E1 is actually nothing but J inverse composite with E. So it is nothing but like J inverse composite with E, and this is nothing but what? This is nothing but Z minus X upon, if gamma minus Y, it is gamma minus Y, right? So what we understood, this is nothing but my E1, which was J inverse composite E. Now as my Z minus Z approaches X, what we know, this thing, this error function should approach towards 0, right? So it should approach towards 0, but we have J inverse also in the composition. So it is J inverse composition 0, so it is 0. Since J is a linear transformation, J inverse is also a linear transformation. Hence J inverse of 0 is also 0. So ultimately, briefly, what I was trying to tell you is my E1 should tend towards 0 whenever my gamma goes towards y. Hence, finally I found that my G inverse of y derivative is actually nothing but what was required. That is nothing but what was required? It was the J inverse. What is J? It is nothing but J inverse. Now what is this J? J is same as, my J was same as G dash at x and taking inverse of it. Since my G of x equal to y, my x was same as G inverse of y. So I replace this x by G inverse. Hence that is nothing but G dash G inverse of y and the whole inverse. And therefore the theorem is true. Therefore the theorem is true for G, and hence what we have proved earlier, that if it is true for G, it must be true for F, right? So I put my best effort to make it as simple as possible. You just go through the video not only once, it will take few times to understand the entire proof, right? Just go through it. At any point if you have any doubt, difficulty, you can let me know with the time. At this time you have some doubt, or at this step you have doubt, okay? And if you like the efforts, if you like the video, if you understood it, please don't forget to subscribe, share with your friends, and like the videos, and put in the comment section what you feel about the video. Your suggestions are very important for me, okay? Thank you so much, and bye bye.